we've just introduced the inverse trigonometric functions, namely arc cosine, arc sine, and arctangent. And these are very interesting functions. They're the inverse functions, not truly to cosine, sine, and tan, but to cosine, sine, and tan restricted to very specific intervals. So just to remind us, the definition of arc cosine is the inverse to cosine restricted to the interval 0 to pi. So visually, that's this first example. The reason we're restricting to 0 to pi is it makes it 1 to 1 and it preserves the range, minus 1 to 1. For sine, we restrict to minus pi over 2 to pi over 2. This middle example in magenta. That's 1 to 1. It's got the same range. We decree that the inverse function to this is the arc sine function. And finally, arctangent is the inverse to tangent restricted to minus pi over 2 to pi over 2. So we're basically restricting this kind of middle s which goes through the origin. So we want to understand these functions. These are really interesting functions. They're delicate because they are inverses to not truly cosine, sine, and tangent, but they are inverses to very specific restrictions. I should also say, as I said last time, these restrictions are arbitrary, right? There's no natural reason to choose them, really. It's a convention that we've decided on as mathematicians and scientists that everyone agrees on. Okay, so let's look at the general properties of these. So let's break it up into the three cases, because we've got three different functions. So let's have the arc cosine, then the arc sine, and then the arctangent. So this is how I'm going to set things up. It's going to be arc cosine here. It's going to be arc sine here. And it's going to be arc tan. And I'm not using cos to the minus 1, sine to the minus 1, tan to the minus 1, because our notation can easily get mixed up with the reciprocal, right? So we don't want to use that. I don't want to use that. Sometimes, I mean, many textbooks use it, but I'm avoiding it. Okay, so let's think about graphs. Now, these are all inverse functions, aren't they? And if they're inverse functions, then if I know what the graph is of the original function, I can graph the inverse by taking the reflection in the line y is equal to x. This is something we've studied in detail already. So let's start off with the restricted graphs, shall we? So the restricted graph for cosine is this, isn't it? So I've got to kind of do my best to draw it. It's this guy. It's this. Okay, so I've got 1 here, I've got minus 1 here, and I've got pi over 2 here, the cross, and I've got pi here. Okay, so this is the restriction. And let's use our usual notation for inputs and outputs. So we'll not use theta anymore, let's use x and y. Okay, so that's my graph of cos restricted to, so that's not that best, let me try and improve it a little bit. So I want to make it as kind of reasonable as possible. So it looks like this. Disaster. It's pretty reasonable. So it looks like that. So that's my y is equal to cos x, right? Restricted. So what does the arctangent have to look like? Well, remember what we're going to do, right? This is the function. The arctangent is going to be the inverse to this. So we're going to draw the straight line y is equal to x, and we're going to reflect this picture in it. And I think this, of all the arc functions, is probably the most confusing to wrap your head around, but let's kind of go through it. So we're going to restrict this, or we're going to, reflect in the line I just drew a second ago, y is equal to x. So let's kind of think about what that would have to look like. Okay, so what does it have to look like? Well, first of all, if I reflect in this line, so I'm going to keep it up here a second. If I reflect in this line, so I'm reflecting across it like this. Well, that's going to kind of reflect the pi and the pi over 2 from the x-axis to the y-axis, isn't it? Right. So let's put those up there. So let's have pi here. And let's have pi over 2 here. What's it going to do to the 1 and the minus 1? Well, that's going to move them to the x-axis. So I'll have a 1 here and a minus 1 here. Okay, so let's take a few points just to get our bearings. This position here, that position there, is going to map down to this position here. Yeah? Now this position here at the end, so at the end here, this guy, where's that got to go? Well, that's the position pi minus 1. So that has to go to minus 1 pi. So it's going to have to map up to the top corner here. It's going to be the reflection. This position, that's pi over 2, 0, so it's got to go to 0 pi over 2, so it's going to have to go there. So if you go through the procedure carefully, what it has to look like is the following. So let me try and draw this as best as I can. It's going to look like this. Can I draw it nicely? It's going to look like that. So it's not so easy to see, but that is the reflection of the above line, or the above graph, in this line. So this is y is equal to arc cosine of x. That's the graph for it. I think this is one of the more difficult examples, because that reflection is pretty hard to wrap your head around. But, and I'll tell you this from experience, it is ridiculously important that you internalize that graph. The shape of that graph, the properties of it, you can see everything about it from the graph really, but you need to internalize this. I have given countless midterm and final exams where a question has relied on understanding a simple property of arc cosine, and if a person can't write down this graph, they're in big trouble, right? You're hopelessly lost. If you can't even describe the shape of arc cosine, how are you going to answer a complicated question about it? So let's do arc sine now. So arc sine, so the same basic story. So I'm going to steal the axes again. So what have we got? Well, in this case, I think it's a little bit easier, because you've got your positions, you've got pi over 2, you've got minus pi over 2, you've got your 1, the scale isn't really perfect, or minus 1, sorry, and you've got 1 up here, and this is what you're going to have to reflect, right? So you've got your sine, so it looks like this. That's what it looks like. So that's what you're going to have to reflect. Okay. So reflecting that guy actually isn't quite as horrifying as it might seem. So this is your y is equal to sine x. Okay, restricted to your interval, closed bracket, minus pi over 2 to pi over 2. So again, same story. We're going to reflect this reflect in y is equal to x. So it's going to look like what? It's going to look like, I've got to get my head straight here. It's going to look something like this. The scale is a bit off for obvious reasons, but you're going to reflect in something along those lines. So this isn't going to be so difficult, relatively speaking. So in fact, I'm going to put these over here before I have to redo this. Okay, so what have I got to do? I've got to reflect in that line. This one is quite straightforward, I think. It's going to look like the following. So again, kind of the x and the y axis are flipped when you reflect. And what you're going to get is you're going to get 1 here, minus 1 here, minus pi over 2, pi over 2. And the shape is going to be the reflection. Not so difficult to imagine what this looks like. It's going to look like this. That's the basic shape. For all exactly the same reasons when it comes down to it. So it's very similar looking. It kind of turns up to become vertical towards the ends, but that's the basic procedure. So this is y is equal to the arc sine of x. As I said, it's vital you internalize this graph. And the way I would say, so the way I do this, is I don't really memorize the graph. I just remember where it comes from. And I remember that I really know what sine looks like. So that's the kind of the graph that we're really familiar with, is the sine graph. And I know what I'm restricting. I'm restricting between minus pi over 2 to pi over 2, and I know I'm reflecting. So I kind of trace through in my mind each of those individual steps when it comes down to it. And you've got to do this a few times to internalize it, but it's really important that you're super familiar with that graph. So finally, and this one again, it causes a huge amount of problems for people, but actually in many ways it's the easiest. So let's draw these kind of two critical kind of positions. So pi over 2 and minus pi over 2. So what does the tangent look like? Well, I'm restricting to between these two. This is what I've got, right? So this is y is equal to, does it equal to the tangent, tan of x. So now what am I going to do? Well, same exact story. I'm going to take this and I'm going to reflect it in this straight line. So it's a bit of a pain that I'm writing this with the same notation, but so this is my y is equal to x in all situations. Y is equal to x. So it's a shame I'm doing it in the same color. In fact, for this specific example, let me change the color of the tangent. I don't think there's any harm in doing that. What's a good color? Orange. Oh no, we've gone too far. So yeah, this is a good plan. Let's change it to orange so that we don't confuse it. So I've got to reflect this. Now, this is definitely a bit confusing, and I can appreciate why people struggle with this. So what we're going to do is, same story as before, reflect in the blue line. So we need to reflect in y is equal to x. Okay, so what does that do? So I think it's worth thinking about these grey lines first, isn't it? So just for a moment, if I took this straight line, so where are we? If I took this line here and I reflect it in the line x is equal to y, what do I get? Well, first of all, this position stays the same, of course. But now when I reflect it, it's actually going to become horizontal. That would be the reflection, wouldn't it? So these two vertical lines, when I reflect them, are going to become horizontal. So that means I'm going to get, when I reflect this, and I'm going to write these in because I think this is a good idea to see them. I'm going to get two horizontal lines, one at pi over 2 and the other one at minus pi over 2. What about everything else? Well, everything else is going to follow the same basic pattern. And it's going to look like this, right? You're going to have kind of a natural reflection like this. Dot, dot, dot. So this is going to be our y is equal to arc tangent of x. All right, so Like I said, I think a lot of people struggle with this one, and I think a part of that, or multiple reasons, but a part of that certainly is the fact that reflecting this is quite confusing. Even if you know it's the reflection, it can still certainly cause problems. But this is lovely, right? This is a really beautiful, beautiful thing once you've internalized all of the different pieces. So the arctangent really does look like a proper elongated S now. So the tangent's kind of like an inverted S almost, but the arctangent is an actual proper S. I don't like it too much. Let me make it a little bit nicer. It's going to look like this. Ooh. There we go. So these are the three graphs: arc cosine, arc sine, and arctangent. I can't stress enough how important it is you are able to draw these. If you cannot draw these graphs, you will not be able to answer difficult questions about these functions. And I tell this to a lot of my students when talking about things like arc cosine, arc sine, arc cos, and things like laws of logs as well. Just ask yourself, can I write them down? Can I write them down cold? Right? If I was asked by my professor to write down the laws of logarithms or what the shape of the arc cosine, arc sine, or arctan graph are, if you can't do that cold, that's a problem. These are going to be bedrock knowledge for you, right, when it comes to calculus. And if you don't have these pieces of information really locked into your mind, it will definitely be a problem. So with these graphs, hold them in your mind for as long as you can, right? Before you go to bed, ask yourself, what is the shape of the arc cosine? What are the key bits of it, right? Where does it start? Where does it end? What's the biggest? What's the smallest value? What's the shape, right? So you need to get to the point where you can do these pretty cold. And honestly, I sometimes forget the shapes. Certainly for arc cos, I think that one's pretty weird. And I kind of have to internally go through this procedure of thinking through, well, what am I restricting to? What's the reflection? And it takes a bit of time. But it's a good idea to really make sure you kind of internalize these shapes properly. So that's just a general piece of advice about these core functions we're going through. Is you need to really know the shapes of the graphs cold. You've got to know them, right? They've got to be really easily at the, kind of the top of your mind when it comes to this, right? Because if you're doing, like I said, really difficult questions in a test, for example, and you don't know the basic shapes of arc cos, arc sine, and arctan, you're going to really struggle, honestly, right? So you need to make sure that you take a lot of time thinking about these different shapes. So with these graphs, we're kind of in good stead, right? We can read off a lot of information. So let's go through all the kind of the basic things that are obvious here. So domain. So all we've got to do is look at the appropriate inputs. Well, this is pretty obvious. This flips, remember, the domain and range of the inverses, and the range of the cosine is -1 to 1, so the domain becomes the same. So, same thing is true of the cosine. And now very, very different. For arctangent, it's everything, because the range of the tangent function, even the restricted tangent function, the way we've set it up, is all real numbers. The range now, well, this now is what? So this definitely can be confusing. For arc cosine, it's 0 to pi. So the possible outputs is 0 to pi. We're going to see why this is so confusing in a little bit. But that's the deal, right? Because you've made that restriction. We've artificially made that restriction on the domain of cosine. Sine, again, closed interval, -pi/2 to pi/2. You can see it directly above. Finally, now this one's interesting. It's obviously not everything. You're restricted to the open interval from -pi/2 to pi/2 because that's the restricted domain of the tangent function when you're defining the inverse. Beautiful. So anything else? Well, yeah, we can see that the increasing and decreasing properties are pretty obvious. So the arc cosine function is visibly decreasing. decreasing. The arcsine is increasing. So when I write increasing here, I really mean overall on the entire domain from -1 to 1. And arctangent, same deal. Increasing. Nice. Increasing. What about symmetry? So symmetry, very interesting. We can see certainly the arc cos has no symmetry, not appropriate symmetry. This is something that I think is easy to get confused about, because you might think, well, cosine is even, so maybe the arc cosine is even, but that just isn't true at all. It's not how it works. So this is neither odd nor even. Whereas arcsine, rather interestingly, is an odd function because, well, it's because sine is odd, and also because of the restriction we've placed on the domain. So this is an odd function. You can see it by rotating around, right? If you took this graph and rotated it by half a revolution, it would stay the same, which is what you're looking for. And actually the same thing is true here. So by our choice of restriction on the domain and the fact that tangent is odd, this is also odd. Very nice. And the last thing I'll say is zeros. From my experience, the only one that causes problems is the first, just because it's a little bit weirder than the others. So here, arc cos of x is equal to 0 if and only if, you can see it immediately above, if and only if x is equal to 1. It's the only point that touches the x-axis. That I always find a little bit confusing myself. It requires a bit of thought. Important you know it. The other ones are more straightforward. Arc sine of x is equal to 0. If and only if what you can see at x is equal to 0. And the same with arctan. Not much else to say, really. You can see that, obviously, the arc cos and the arc sine are bounded. Well, actually, they're all bounded because their ranges are bounded above by, for example, 2 pi, and they're bounded below by 2 pi, or minus 2 pi. Okay, so there's not much else to say about these. I think, as I've said repeatedly, by far the most important thing here is having the graphs internalize, understanding where they come from and understanding their shapes so that you can draw upon this information quickly when you're being asked difficult questions about it is really, really important. That's the key to doing well in all sorts of kind of calculus applications of the inverse trigonometric functions.